Welcome to Lecture 8.3 in Math 1324, Introduction to Probability. So if you go to a pizzeria and order 2 large pizzas at $14.99 each, you can easily find the exact price of your purchase, which is $29.98. For the manager at the pizzeria, however, it is impossible to predict the exact number of pizzas to be purchased daily. The number of pizzas purchased during a day is random. The quantity cannot be predicted exactly because you may not sell the same amount of pizzas today as you sold yesterday. A great many problems that come up in applications of mathematics involve random phenomena for which exact prediction is impossible. The best we can do is determine the probability of the possible outcomes. So let's look at some vocabulary. A random experiment, sometimes called a random phenomenon, has outcomes that we cannot predict, but that nonetheless have a regular distribution in a large number of repetitions. Okay? We call a repetition from a random experiment a trial. The possible results of each trial are called outcomes. I'm going to give you an example in a minute, so this will explain. For instance, when we flip a coin, the outcomes are heads or tails, right? Every time you flip, you're either going to get a head or you're going to get a tail. We do not know whether a particular flip will yield heads or tails. Could be either. But we do know if we flip a large number of times, about half of the time there will be heads and about half of the time there will be tails. And each flip in this case is called a trial. Each time you flip the coin, it's called a trial. The sample space, denoted by the capital letter S for a random experiment, is the set of all possible outcomes. For the coin flipping, the sample space would be S equals heads, comma, tails. So notice this is set notation and listing all the possible outcomes from your experiment or trial. Give the sample space for each random event. A, we have a spinner here. So when you spin, what possible places will it land? Well, we can see here that there's numbers 1 through 7 on the spinner, so the sample space is 1, 2, 3, etc., all the way to 7. Let's look at something a little bit more complicated. For the purposes of a public opinion poll, respondents are classified as young, middle-aged or senior, and as female or male. So what are the possible outcomes? Now you got to think. So I could have a young male or a young female. I could have a middle-aged male or a middle-aged female. I could have a a senior male or a senior female, etc. So in this case, I have to kind of look at the combinations of the two different elements that people are asking. Okay? Give the sample space for each random experiment. We're continuing this. An experiment consists of studying the numbers of boys and girls in families with exactly 3 children. Let B represent boy and G represent girl. Now we have 3 kids in the family. So it gets a little complicated because the first kid can be either a boy or girl. Well, the second kid can be a boy or a girl too, but remember that the first kid was a boy or a girl, and the second kid is a boy or a girl, and the third kid can be a boy or a girl. So I have all these different combinations because I could have boy, boy, girl, boy, 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 girl, boy, etc. So it gets hard to kind of figure these out. And one thing that you can do is create a kind of a decision tree or a tree chart to help you figure out all the different combinations. So our first child can be a boy or a girl. The first child's a boy, the second child can be a boy or a girl, or if it's a girl, it can be a boy or a girl. And then of course the same here, boy, girl. And then all we have to do is follow each path. Boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. That sounded kind of funny to me. And so here are all the options, etc. So this, when you have multiple options, this decision tree or tree chart can really be helpful to make sure that you don't miss any. Draw a tree diagram for the random experiment of flipping a coin 2 times and determine the outspace. So again, here we'd have heads or tails for the first one, heads or tails for the second one. And so what we get is heads, 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 tails, heads, tails, heads, tails, tails. Okay, I didn't draw the diagram here, but you could use this one kind of as a sample just at 2 levels. An event is an outcome or a set of outcomes of a random experiment. Thus, an event is the subset of the sample space. Remember, the sample space is all the possible outcomes. An event is a specific outcome or group of outcomes. Okay? For example, if the sample space for tossing a coin is heads or tails, then one event is heads, which represents the outcome head. So I might try to find the probability that I toss a head. The sample space for the experiment of rolling a fair dice is S equals 1, 2, 3, 4, 5, 6. There are 6 sides on a die, and each side has a number from 1 to 6. So the possible events are the die shows an even number. Okay, so event even number would be all of the ones from the sample space which are even. So we have 2, 4, 6. The die shows a 1. Then we just have the number 1. The die shows a number less than 5. This is a different event. So we have all the numbers that are less than 5. 1, 2, 3, 4. So an event is just a subset and a specific category of outcomes. Identify the event for a family with exactly 3 children. The family has exactly 2 girls. So you have to go back and look at that tree chart and think, which of the solutions had exactly 2 girls? Well, we had 3 situations. We had boy, girl, 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 boy, girl, and girl, girl, boy. The 3 children are exactly the same sex. Well, this is pretty simple. It's either boy, 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 or girl, girl, girl. That was an easy one. And event J was the family has 3 girls. Well, that's easy too. Girl, girl, girl. Okay? So the event, again, is a kind of a subset of the sample space, and it's a way to categorize. The sample space is everything that's possible to happen. The event is usually what we're looking for probability. Hey, what's the probability my second child will be a girl? Kind of thing. Suppose a fair die is rolled. Find the requested events. The sample space is 1, 2, 3, 4, 5, 6. The event, the die shows a 4. Well, that's pretty straightforward. That's just going to be 4. The event, the number showing is less than 10. Okay, now this is confusing. Okay, so would it be 1, 2, 3, 4, 5, 6, 7, 8, 9? No, because remember, the event is a subset. It can only use the possible outcomes. You cannot roll a 7 with 1 die. So in this case, this event, the event is the same as the sample space because all of the outcomes in the sample space are less than 10. The event, the die shows a 7. Again, a die cannot show a 7. There's not a 7 on a die. So in this case, we call this, this is the empty set. There is no event that this will happen. And it's also called an impossible event. Okay, it's not possible for it to happen. Let's look at some set operations. And this is really important, so pay attention. Make sure you put this down in your notes. Let E and F be events for the same sample space S. E intersection F, E and F E intersection F, E and F occurs when both E and F occur. So they both have to have the same member. That's the intersection. E union F occurs when E or, this is E or, union is or, intersection is and, occurs when E or F or both occur. Okay, so if it's in E, it's part of this. If it's in F alone, it's part of this. If it's in their intersection, it's part of this. E apostrophe is read as not. E not occurs when E does not occur. So for example, if event E was that you roll a fair dice and the number is even, then E naught would be the numbers that are odd. It's the opposite. It's the opposite of whatever the event is. It's all the members of the sample set that are not in event E. Okay, this is a good one. A study of college students grouped the students into various categories that can be interpreted as events when a student is selected at random. Describe each of the following events in words. The student is under 20 years old. F is the student is male. And G, the student is a business major. Okay, those are your givens. Now describe these. E not. So E is that the student is under 20-year-old. Did you say the student is over 20? If you did, you got it wrong. Why is that wrong? E is that they're under 20. So E not would be that they are 20 or older, right? Because 20 is not included in event E, so we have to include it in E naught. So be careful. Sometimes our knee-jerk of doing what's not there is with language. The opposite of under is over, but this is 20 or over. So be careful. Let's look at B. F naught intersection F naught and G. F naught is male. I'm sorry, F is male, so F naught is female, okay? Remember that both of these have to occur for intersection, and G is a business major. So we're looking for a non-male business major or a female business major. Of course, in today's day and age, with gender language, this could be a little bit more complicated event, okay? But here we're going to keep it simple. This is a female business major. All right. E naught union G or E naught or G. Again, we said E naught is someone that's 20 or over. G is someone that's a business major. Now remember, when we have or union, it can be either. So we can have a student that's 20 or over and any major, or we can have a business major. The student is 20 or over or is a business major. This also includes all students 20 or over regardless of major, which is what I said initially. Two events that cannot both occur at the same time, such as getting both a head and a tail on the same toss of a coin, are called disjoint events. Disjoint events are sometimes referred to as mutually exclusive events. When you're rolling a die, if event E is to roll an even number and event O is to roll an odd number, another example, you cannot roll a number that is both even and odd. So they are mutually exclusive events or disjoint events. Events E and F are disjoint events if E intersection F equals the intersection. There's no common member. There's no common member. For any event E and E naught are disjoint events. That's by definition, right? E naught is everything that's not in E but is in the sample space. Let the sample space equal 1, 2, 3, 4, 5, 6, the sample space for tossing a die. Let E equal 4, 5, 6, and G equal 1, 2. Are E and G disjoint events? Are there any members in common between E, 4, 5, 6, and G, 1 and 2? No. So they are disjoint events because there's nothing in common. They're mutually exclusive. All right. We've had a good 15-minute run. We're about halfway through these video and presentation lecture. So I thought we'd take a brief pause. I think these pauses in the middle would be a little bit more helpful. So you can just stop this now if you want, go get a drink, go take a walk, go do a TikTok dance, etc. So I found this recently on my phone, 10 ways to show up for yourself. You've got to me, it's really important that we all remember that our first priority is to ourselves. That sounds a bit selfish, but we need to take care of ourselves first. We need to find our place in the world, what our passion for work is in the world, what our gifts are, etc. And we better serve other people in the world by first paying attention to ourselves and again looking at our passions, etc. So these are some recommendations for how do you take good care of yourself and how do you live your best life, if you will. Number one, commit to habits, practices, routines, and rituals that are good for your well-being, even when you don't want to. It's well documented that it's our habits that create our life, that it's our habits that influence us the most, the things that we do regularly. You don't become obese because of, eating too much in one meal. It's a habitual thing. You don't become, svelte and strong by going to the gym once in a while. You do it as a habitual thing. Your habits for well-being are probably not the same as my habits. And so it's really important for you to figure out what kind of life you want, what kind of experience you want, what kind of situations you want to be in, and then try to find habits that can help you build that life. Number two, allow yourself to feel a multitude of feelings without labeling it as wrong, bad, or negative. Great quote is, feelings make great guides, but horrible masters. Your feelings are alerts to you. If you're really angry, it's letting you know something is upsetting you, okay? How you act to it, you don't want to just allow that anger or sadness or whatever to be in charge, the master of what you do. For example, when someone cuts you off in traffic, I get angry or frustrated. And, if I allowed that anger to be my master, it might say, well, screw that, I'm going to wreck my car into him. Well, that's not going to serve me in a good way in the long run. It's going to cause me more problems and more frustration than letting that go. So it's important to pay attention to it, acknowledge it, whatever your feelings are, and then, decide how you want to react to them. Number three, practice listening to your needs and discovering different ways of meeting those needs. This is a big one because we're so distracted now between TV, social media, and really our phone. Our phone is the number one distraction that we hardly ever listen to ourselves. Turning things off and really thinking about what kind of life do I want to lead? What do I need in my life? What is the most important thing for me to be doing to get what I really want, not to just go through the motions? Number four, practice self-forgiveness for not being perfect, for forgetting, for your past, for what you don't know, and for getting off track sometimes. You will screw up. You probably screwed up in this class and you'll probably screw up again. You're going to make mistakes. I'm going to screw up. I've made mistakes in this class and I'm going to make mistakes again until the day I die. Being gentle with ourselves, moving through those mistakes. I see people get so frustrated when something, happens to them or, that they've caused some problem. And interestingly for me, travel has really helped with this because you can't control a lot of things in travel. And it's kind of given me this, because I've traveled a lot and hiked a lot and done long hikes, it's kind of given me this kind of attitude like, if I don't like what I see, then I'll go around the corner. There's another corner coming up. And, when bad stuff happens, you just have to walk through it. And if I get really down on it and frustrated, it's not really going to help me get through it. Let yourself start again, over and over as often as needed. We think that quitting is bad, but sometimes quitting is the best thing for us. to quit and start over, to quit and try over, to withdraw from a class. I took too many classes, okay? But quitting one class doesn't mean I'm a bad person or I'm a loser or I'm a quitter. It means that it may be in my best interest that I made a mistake in selecting that class or how many, and it's time to let that go. Take care of your basic needs, stay hydrated, get enough sleep, move your body, and eat plentifully. One of the most basic things, again, going back to habits, this should be number one in my book. You don't need to belong to a gym or lift hundreds of pounds of weights to be in great shape. Honestly, walking for an hour a day would create a healthy physical and even mental being for most people, especially if you leave your phone behind and you're not texting and all that crap while you're walking, but just walking out your door. It doesn't cost anything. Walk through your neighborhood. You can get an easy app on your phone called Map My Walk. That's so you can kind of check your pace and, over time increase your pace so that it increases the health benefits. Find habits, simple habits that you can do on a regular basis that you're not resistant to doing, resistance to going to the gym, etc., that really kind of feed you and take care of you. And walking to me is one of the most important. In America, we go everywhere by car. It's part of our culture, and so we don't walk as much as people in other cultures. And yet, this is one of the easiest and most healthiest things you can do. And for me, once you start doing it and made it a habit for a month or so, it's the most enjoyable. It's fall right now when I'm recording this, and this is my favorite time to walk. The colors are awesome. I walk right outside my door, and I walk an hour. It's about 5 miles. And just walk through neighborhoods, etc. Maybe you're lucky and live near a park or a trail, and that can be even better. Number 7, give yourself permission to rest, to take breaks, and to have downtime. Really important as a student. If you're going to block out 4 hours to study, then make sure the last 10 minutes of every hour is a break. Walk out, have a drink, do a jumping jack, do a TikTok dance, text your friend, whatever, play a game. Take breaks frequently. Do work in small periods and give yourself rest and breaks, and to have downtime. Make sure that you try to give yourself a day off, maybe a week if you can. Spend quality time with yourself, reading, writing, creating, and getting to know who you are underneath who you think you should be. I think everyone should have a creative outlet. Maybe it's cooking, maybe it's decorating, maybe it's reading, maybe it's writing, maybe it's drawing, but making a plate, I don't know. Creativity and building things, creating things, it really, I think, feeds our spirit. Before there were so many of us and we all have these specialized jobs, people were artisans. Whatever you did was your art. Your work was your art. You built cabinets, or you built pottery, or you were a farmer and you grew food, etc. So try to, think about what feeds you spiritually, mentally, etc. And know that your habits, like most of us are so habitually tied to our phone and social media and media in general, that when we try to do things like read a book or read something or change our habits, we're resistant to it. Fight through that resistance, because if you get through it, you might realize, I really enjoy reading better than I do, playing Mind Tap on my phone or whatever the hell you play. All right. Use a lens of curiosity and compassion with yourself as often as possible. Asking yourself questions, about where you want to be, where you want to go, how do I get there? It's everything in life is step by step, piano, small steps. So constantly asking ourselves, what's going on? What do I want to be doing, etc. is really key. There's a poet, I think it was a German poet named Rilke, and he said something like, most people try to focus on the answers. They try to answer questions. He goes, but the key is to figure out what are the questions for your life, and then allow life to provide you the answers. And so if you figure out what the big questions are, that's more important than trying to get an answer or to figure it out. Ask yourself the big question, what am I here for? And allow life to show you the answer. So maybe the questions are more important than the answers, and maybe that's what number 9 is about. Remind yourself that you're as worthy of being shown up for as anyone else in life. Make yourself a priority in life. You need to make yourself number one. You need to make yourself number one. All right, it's time to move on. So now back to probability. So we've learned some vocabulary in probability, some concepts, and now we're going to actually learn some calculations. The way to calculate probability is by using the number of elements in an event and the number of elements or possible outcomes in the sample space. So if we let S be the sample space of equally likely outcomes and let E be a subset of S, the event, then the probability that event E occurs is the number of elements in event E, the number of outcomes, divided by the number of outcomes in the sample space. The probability of event E equals the number of outcomes in event E divided by the number of total outcomes in the sample space. By this definition, the probability of an event is the number that indicates the relative likelihood of the event. How likely is something to occur? The basic probability principle, or this calculation, applies only when the outcomes are equally likely. So, if you're rolling a fair die, then 1 through 6, getting any of them is equally likely. A loaded die is a die that's been weighted to to land on other numbers more often. And so this probability would not work. So let's look at an example to make this clear. Suppose a single fair die is rolled that has a sample space of 1, 2, 3, 4, 5, 6. Give the probability of each of the following events. The die shows an even number. Well, there's 3 even numbers, 2, 4, and 6 in this event, E, and there's 6 outcomes in the sample space. So our probability of rolling an even number is 3, the number of outcomes that are even, divided by 6, the total number of possible outcomes, or 1/2. And we do view this as a fraction, and we do reduce it. The die shows a number less than 10. Well, the event F has 1, 2, 3, 4, 5, 6 possible outcomes, because all of the outcomes in the sample space are under 10, so all of them. The sample space also has 6, so our probability that F will occur is 6 divided by 6, or 1. When you have a probability of 1, this is called a certain event because it will happen every time. You are certain that this event will happen. When you roll a dice, when you roll a die, you know that every time you're going to get a number less than 10 if you're rolling one die. The die shows an 8. Well, there are no members in the sample set, in the event outcomes, because no die has a number of 8 on it, and there's 6 in the sample space. So we have 0 divided by 6. This is not undefined. Remember, it's undefined if 0 is in the denominator. So we get the probability that G will happen is 0. There is 0 likelihood this will happen. This is called an impossible event because it will not happen. It's not possible to roll an 8. It's not possible for this event to happen. So these are a couple of insightful things. If your probability is 1, then you're absolutely certain that something's going to occur. If your probability is 0, then you're absolutely certain that something will not occur. All right, so we're going to look at a deck of cards. We're going to get some more challenging probabilities here. A standard deck of 52 cards has 4 suits: hearts, clubs, diamonds, and spades, with 13 cards in each suit. The hearts and diamonds are red, the spades and clubs are black. Each suit has an ace, a king, a queen, a jack, and cards numbered from 2 to 10. The jack, queen, and king are called face cards. And the ace, it can be thought of as either a low card, a number 1, or a high card, an ace, higher than all the kings. Okay, so that's a deck of cards. And here you can see it visually as well. There are 13 cards in every suit, ace through king. There are 4 suits, hearts, clubs, diamonds, spades. So there are 52 cards total, 4 times 13. The face cards are jack, queen, king. There's 3 in each suit, so 12 total, etc. All right, if you need to write this down, if you're not familiar with the deck of common cards, then you might need to have this someplace. If a single card is drawn at a random from a standard, well-shuffled 52-card deck, find the probability of each of the given events. Drawing an ace. How many possible aces are there for me to draw? An ace of hearts, clubs, diamonds, and spades. So the number of outcomes in this event is 4, and how many cards are there total in a deck? 52. Okay, so there's 4 aces. There's 52 possible outcomes when I'm drawing a card. So I have a 1 in 13, a 1/13th probability of drawing an ace. Drawing a face card. Well, there's 3 face cards in every suit, clubs, diamonds, hearts, and spades. So that's 12 total, and then there's 52 cards possible. So here we have 3 out of 13. Drawing a spade. Well, there are 13 spades out of 52 cards, so we have a 1 in 4 chance, or excuse me, a 1/4 probability of drawing a spade. Drawing a spade or a heart. Okay, so here we have 13 spades and 13 hearts. It doesn't matter, it can be a spade or a heart. It doesn't say and, it's or. So we just add them up totally, and so we have 26 possible cards that are either spades or hearts out of 56. So we have a 1/2 probability of pulling a spade or a heart. Okay. Hopefully that helped you with some of these calculations. When it's or, you just add them all together. When it's and, we're going to look at that in more detail. For any event E, the probability of E has to be between 0 and 1, and that's all this is saying. If it's impossible for it to happen, it'll be 0. If it's guaranteed to happen, it'll be 1, and it can fall anywhere in there. So probabilities in general go from 0 to 1, inclusive. In many real-life problems, the events in the sample space are not all equally likely. When this is the case, we can estimate probabilities by determining the long-run proportion that an outcome of interest will occur given many repetitions under identical and independent circumstances. We do this often when we perform a statistical study. The long-run proportion is called the relative frequency probability. Estimates based on relative frequency probability are sometimes called empirical probabilities. Independence in this context refers to the idea that what occurs in one run has no effect on the outcome of a subsequent run. So let's look at an example, and I think this will help you clear it up. For example, imagine that we want to determine the probability that a newly manufactured porcelain sink contains a defect. We examine the first sink before it is shipped and see that it has no defects. So we estimate the probability of a defect as 0 because the relative frequency of defects is 0 out of 1 trial, and you can see that here. The second sink, however, has a defect. Now our number of defects is 1 out of 2, so our relative frequency is 1 out of 2, which is 0.5. You can see that here. The first one had no defects, then we had a defect. Now we're going to look at 10 sinks, and then we had no defects. So now we had 1 out of 3, right? And no defects, 1 out of 4. No defects in the fifth, 1 out of 5. But the sixth had a defect, so we had 2 out of 6, or 1/3. Seventh had a defect, so we had 3 out of 7, or 0.43. And then no, and we get up to 3/10 and back to 0.3. So the idea here is that we can we use this relative frequency probability to kind of show what's happening over time. And you might think of this like when you shop online and you see the number of stars or ratings that people have. This is kind of a relative frequency thing, like how much do people like this? How reliable is this product? It's not truly statistics, but it's a similar prospect that you're using data from people that, 75% of the people gave it 5 out of 5 stars. Only 2% gave it 1 out of 5 stars. So it's a greater likelihood that this will be a good product. Okay, and so that's kind of the concept behind this relative frequency problem. Notice that the relative frequency fluctuates a great deal. We started at 0 and immediately went to 1/2. So like first we have 0 defects and now half of the products have defects, and then we have a third and then a quarter. Then we get up to almost a half again. So there's a lot of fluctuation early on when we're doing these relative frequencies. So to get a better estimate of the probability of a defect, we need to examine what's called the long run proportion of defects. Not examine 10 of these sinks, but maybe 50 of them or 100 of them or 1,000 of them. When the same conditions are repeated a large number of times, the relative frequency will stabilize to the long run frequency. In a way, like I said, you can think of this kind of like ratings when you go on Amazon and shop. Maybe you look at a product and you see how many stars it has. And maybe the product that you're interested in has 4 stars. But when you look at the number of people who have rated it, there's only been 4 people rating that. So it might be smarter to pick a product that has 3.5 stars, but that has 500 people rating it, because that is more reliable. It's more probable that those stars are accurate the more number of people rating it. And that's the same idea that we have here with the relative frequency and long run frequency. Okay, so we're going to look at 2 figures. Figure 821 shows how the relative frequency stabilizes to some degree after 50 trials, and then 822 shows after 1,000 trials. So let's look at those graphs now. So here we can see 821, and you can see the frequency early on when between 1 and 5 we're going up and down and up and down, and a little jigsaw here. But then it starts getting closer and closer to some line. When we look at 1,000, we can see that, once we get out beyond 100 or 200, 300, 400, it really almost becomes a solid line. And so we get this long run proportion of defects is close to 0.25, which is saying that about 1 in 4 sinks has some kind of defect in it. Okay, so that's why we do this long run. If we stay with only 10, we don't have a good estimate. But the more tests or trials we run, the more relative frequency and stabilization we get. All right, let's look at an example. The General Social Survey picks U.S. residents at random and asks them a great many questions. One of the questions they asked respondents in 2012 was, do you feel your standard of living is much better, somewhat better, about the same, somewhat worse, or much worse than your parents? The responses are here below. So here's that survey. Estimate the probability a U.S. resident feels his or her standard of living is much better than that of his or her parents. So we know that's the event, right? Much better. There's 413 responses to that. But how many total responses are there? That would be our sample space. How many total respondents were there? Well, we have to add all of these up, okay? So we get 413 out of this 1,308. That's if you added up all of these responses. And so we get a probability of 0.3157, which is about 1 in 3 people. So try B and see if you can get that one. Estimate the probability of the event V that a U.S. resident feels that his or her standard is somewhat worse or worse. Okay. Now this is bad language because there is no worse, but we're going to have to do somewhat worse or more worse. That's kind of funny. So we're going to look at these second two. You're going to add these numbers up. This will be your numerator, and the denominator will be the same. It's the sample space or the total number of trials or people surveyed. And you can see that there. So the last thing we're going to touch on here is the properties of probability. Let S be a sample space consisting of n distinct outcomes. S1, S2, S3, etc., up to S sub n. So we have a sample space with n different outcomes. An acceptable probability assignment consists of assigning to each outcome a number, each outcome S sub I, some subletter, a number P sub I, which is the probability of S sub I, according to the following rules. We know that the probability of any outcome is between 0 and 1. So P sub 1 is between 0 sub 1, P sub 2 is between 0 sub 1, all the way up to P sub n. This is just a rule for any probability. However, when we think about all of the outcomes that are in the sample space, then all of the probabilities for each of those outcomes has to add up to 1. Now, what is this saying? It's saying that if we look at the rolling a fair die again, and there's numbers 1 through 6, the probability of rolling a 1 plus the probability of rolling a 2 plus the probability of rolling a 3, of a 4, of a 5, of a 6, all of those together have to add up to 1. Well, that makes sense, right? Because if I add up all the probabilities for every single outcome, well, then I'm counting on a certain event because it has to be one of those possibilities. And so that it's got to be one of all of those probabilities. And we know that when the probability equals 1, it's a certain event. So when we're talking about the probabilities of possible outcomes, the sum of them has to add up to 1. Alrighty, that's the end of our lecture. I'm sorry it's a long one, but we had a long kind of pause in there. Have a great day and reach out if you need anything.